Hi everyone, welcome to Monster Scale Summit and to my session, Reduce Your Cloud Spend with ScyllaDB. I'm Tzach Livyatan, VP Product at ScyllaDB, and this is my picture from 10 years ago. Today we're going to cover reducing costs in three parts. The first will be reducing costs with ScyllaDB core, the database itself. I will talk about database properties that help you reduce cost, mostly performance. The second will be reducing cost in ScyllaCloud. ScyllaCloud is a specific version of Scylla or a hosted Scylla as a SaaS, as a web service. And we'll talk about reducing cost with ScyllaCloud, and that will cover different properties of the database and specifically for the cloud. And in the third part, I'm going to talk about things that we just achieve or will achieve soon, a new feature, a new pricing plan. I hope to make it interesting. So let's get started, and we'll start with reducing cost with ScyllaDB core, the database itself. So ScyllaDB is a database that was designed from scratch with a thought about performance. And when I'm talking about performance, I'm actually talking about two different properties. One is latency, how much it takes for each response to return from the database to the application. When we're talking about Scylla, we usually talk about sub-millisecond latency. Latency is super important for many applications in EdTech and many other, but it's going to be out of scope for this presentation. If you are interested, there are other sessions in the summit more focusing about that. The other part of performance that I will talk about is throughput. Throughput is the number of requests a database can serve in a second, and in particular, it's super important for cost because the more throughput you can take from a core or from a computer, the less computer or server that you need, and that's automatically reduce your cost on the cloud. It's a very direct function from throughput to cost, and Scylla use unique technology in that it can support many requests per core. It can support many core per machine, and it can support many machines or many nodes. Scylla can grow in a high available deployment up to hundreds of machines. I don't think anyone got to that because each machine is very strong as well, but we do have 50 and even more nodes across multiple regions. It can easily support a newer server with a lot of cores. We'll talk about this a little bit later. And you see the information here, 60 terabyte. It can support from very small nodes to very beefy nodes, and actually combine them, and that's one of the unique things I will talk about later. So some of the design decisions that made Scylla a good choice for performance. I'm not going to cover all of them. I'm not going to cover the C++ instead of Java, for example, because I know it's a touchy subject for many. So I'm going to jump directly to sharper code, which I consider the most important design decision that was made back when we started with the Scylla project. So in many applications, or legacy application, I might say, either written in Java or C++ or C, the way that the software is architected is many threads, and these threads are competing with each other for access to the storage, access to the network, and access for memory. If two threads need to go to the same area in the RAM, the same area in the memory, they will take a lock usually or synchronization, and that's take time. That's take out of the performance. And actually, when we do profiling or did profiling of such application, we found that a huge amount of the CPU is wasted on thread context switch and thread waiting for each other. So one of the main decisions that remain till today is in Scylla we have one thread per core. We call it one shard per core, and this thread is pinned to the CPU and never context switch. And this leads to a lot of other architectural design, like all message between threads is based on message passing. There is no lock-in. All work is asynchronic with the storage and with the network. And that's, I think, the key to high performance. By the way, since we started, other projects adopt a similar approach as well. If you look at Red Panda and others, they are using similar technology. Unify cache. So Scylla try not to rely on the OS for performance and for decision. We'll see it later in storage. This is about the RAM or the cache, and try to manage all the computer resources, all the server resources itself, including the cache. So definitely we're not using the Linux page cache, because it's not optimized for database, and we allocate half of the memory for cache. Other part of the memory are used for memtable and an operating system and other, and half of it usually for cache, and we can control both if we want to shrink or enlarge the cache base on the use case, but also which values are in the cache and which are not. And this is, if you're interested in database, I recommend you following Andy Pavlo, and this is one of his interesting posts about mmap and its use in databases. So very much related to what I just mentioned on cache. Check it out later. One more interesting or important decision that we made with accessing the storage is about scheduling access to the storage. So first of all, storage is a super important part of any database. You can think of a database naively, but quite accurately as an application that write and read from the storage. So the speed of writing to the storage is super important. And what we found out pretty early, that if the application, in this case ScyllaDB, try to send more and more concurrent parallel requests to the storage, yes, it leads to better throughput at some point, but as you can see in the diagram, at some point you send more and more requests, but the response are going back in the same pace, so you are just filling up the queues in the SSD itself, in the storage itself, and create more latency. And it can happen for read, this can happen for write, sometimes in different pace. So what we do in Scylla is we are not naively throwing a lot of requests to the SSD. Rather, we benchmark the SSD in advance and tune the scheduling of the IO scheduler in Scylla to send just the right amount of parallel requests to the storage to get the best throughput. We try to find this sweet spot, and that's significantly increase the performance. Not only that, it's give the database more control of which request is more important and which is less important. If you let the SSD or the operating system to manage your queues, you cannot control which request is more important than the other. While on database, there are more requests that are more important than the other. For example, a repair or a compaction, we consider it less urgent than a real-time request. Even more than that, we actually expose this kind of what we call workload prioritization to the user, and the user can actually control to some extent what prioritization you want to give to each request. So if, for example, there is an analytic request, usually the latency is less critical. In an analytic request, it can take from a second to a minute, but for real-time request, you always want them to be sub-millisecond. So the IO scheduler allows you to control that. So I try to establish in this small presentation so far that Scylla have a unique architecture that is a design for performance. And again, in this session, when I say performance, I focusing mostly on throughput, high throughput, less server on the cloud, reducing the cost. And the next section, I'm going to cover tablets and then explain how we use it in the cloud. So what are tablets? Tablet is the latest and greatest addition to the Scylla database. We are working on it for quite some time. We introduced it on Scylla Enterprise Release 2024.2, and it will be part, of course, of 2025.1. Tablet is a new mechanism to distribute partition across the nodes. As you probably know by now, Scylla is a distributed database which have many nodes from 3 to hundreds. And Tablet is a new algorithm to distribute the data across the node. Before Tablet, we had an algorithm called vnode, Scylla inherited from Apache Cassandra, which was a static distribution of the partition. And the static distribution only changed when you add or remove node. Tablets are a much more dynamic way to distribute the data, and Scylla, the database itself, can decide to merge tablets, split tablets, move tablets around to try to balance between all the nodes on the cluster, and this have a lot of advantages. On the scope of this session, the most significant improvement is very fast scaling, and I will demonstrate it soon. So this is a visualization, I hope you can see it, of a cluster that is scaling from 3 node to 5 node. You can actually, this is actually closely monitored an actual database. Let me run it again. And you can see that once the new node are added, tablets start to migrate to the new node until the cluster is balanced. So why is it unique and why is it improved scaling time? Last time, because unlike with the previous version of Scylla, here once the first tablet migrate to the new node or nodes, it's already start to serve in request. So you don't have to wait for the entire cluster to balance itself before the new node start to serve a request. Rather, they start to serve request immediately, and that's a huge improvement in performance. This is the same type of information, but presented in a different way. What we see in here is a cluster of starting with 3 nodes and serving something like 17,000 requests per second. Not a huge number for Scylla, by the way. At some point, 3 nodes are added. As you can see here, I'm using my mouse now. As you can see here, the 3 nodes already start serving write request. At some point, the cluster is balanced and all the nodes are serving the same amount of requests, this time with 6 nodes instead of 3. And at around just before 4, I hope it's PM and not AM, we start decommission nodes and the requests per node going back to the original value. So what I wanted to focus here was what happened in 3.15 when the node was added and immediately start serving requests, more and more requests until the cluster is balanced. So we cover up to this point how the core Scylla database can help you reduce cost, mostly by high throughput. And I also hint about quick scaling. Now I'm moving to the second part of the session, Scylla Cloud, and how we use tablet and other feature to reduce cost in the cloud. This part will include 2 mini sections. One is about what we call xCloud, and one is how to reduce network cost. So let's start with the xCloud. What is xCloud? xCloud is, if I can, on a very high level, is taking what we develop with tablets and Raft and other features in Scylla Core and bring this advantage to the cloud. And the project that we name xCloud allow us to reduce cost in 2 main ways. One is just-in-time scaling, and I will demonstrate it in a second or in a minute. And the second is reduce cost with higher storage utilization. These two are very much tied together, as I will try to prove. The last one is more for UX improvement. You can boot cluster faster and boot node faster. So it's actually helping scaling sometime and also just a better UX when you click create a cluster till you get the cluster up and running, which is down to minutes. So I talk about fast scaling and storage utilization. Now I'll show how they're actually tied together and how fast scaling and mixed size cluster allow us to have higher storage utilization. So this is a diagram of the current status of Scylla Cloud. What you see here is 2 lines. The blue line is the actual storage used in the cluster. The red area is the available storage. So this is how a typical cluster will look like. We'll start, and by the way, this is per zone. You can imagine there are 3 copies of each of this entire structure. So we have the initial cluster is already 3 identical nodes and then 6, etc. So but let me focus on one zone because it helped me demonstrate my point. So I4I 16 extra large starts with 15 terabyte. And when this storage is almost exhausted in 70%, the only option was in previous version of Scylla Cloud is add another identical node because the support was not there for different size of node. And each time this storage exhausted, we add another node. So this worked fine, but as you can imagine, there are 2 disadvantages. One, it takes time to add such a large node and stream the data to it, especially before tablet. And second, we are wasting a lot of extra available storage that we are not actually using. And the solution is quite straightforward. This is roughly what we want to get to. So we want the actual storage that we're using to be very close to the storage that we have. So we wouldn't pay for extra storage that we are not actually using. And we achieve that with xCloud. With xCloud, we are able to actually mix and match different instance size to be very, very close to this actual storage. So let's say we are starting with the same type of instance per zone, the 16 extra large. But at some point, actually at 90%, not at 70%, we identify it's close to the edge. So we are adding another small node. In this case, too extra large. After some time, if this node is exhausted as well, we add another one. At some point, we can replace smaller node with a bigger node. But what is important here, what I want to demonstrate, that we can follow with the storage that we are allocating very, very close to the actual usage. This is why we can do the improvement between 70% utilization to 90% utilization. So we are actually reducing the extra part that you don't really need. And of course, automatically with that, you can reduce the number, or we can reduce the number of servers that you are using and save you money. And this continues to grow. A second demonstration of that is actually on compute, not on storage. Unlike storage, is usually very gradual because it takes time to write to the database. It cannot fluctuate by much, but compute can. There is hour in a day that many user, for example, use their application, or you have a batch processing at night or whatever. Every application have this kind of pattern over the day and over the weekend. And so far, since the scaling was not fast enough, you couldn't do much about it. You have to allocate all the resources in advance. But with xCloud and tablet, we can actually allocate and deallocate resources very fast. And like I shown before, try to match the actual allocation to the usage most closely. And of course, that saves cost because you need less server. You don't keep in an extra server just in case. And this is another application usage. Anyone know what this diagram stands for? You can write in the chat and maybe I will get back to it later. Okay, so to summarize the ScyllaDB xCloud, we show how tablet that was added to Scylla Core allow us to do a fast scaling. And with heterogeneous server, we are able, different size of server, we are able to do just-in-time scaling and high storage utilization and save you money by using less server. I hope it's clear. So reduce the network cost, another improvement we introduced in Scylla Cloud. So if you are using Scylla Cloud or other distributed database on the cloud, you might notice that network cost is actually big part of what you pay for. And that actually makes sense because in many databases like Scylla and other, all the data is replicated 3 times, sometimes 6 times. Sometimes you replicate 3 on one data center, 3 on another data center, sometimes 3 data center. And each of these data center, the default deployment is zones. So we are paying for the communication between the zone and the communication between the region, and the communication between the application and database, and it can accumulate. So we are trying to reduce this cost, and we develop a few mechanisms. One mechanism that actually implemented was enabled by the tablet feature is improved file-based streaming. Much more efficient than the previous way that Scylla communicates between nodes. This, as a side effect, allows us to scale faster, but also stream less data when you add node, and this already reduces the network cost by much. A second thing that we implemented in recent Scylla releases is better compression of the data on the wire on the network. Initially, we have LZ4 compression, and in latest release we moved to ZSTD and ZSTD with dictionaries. I have to say the compression depends on the workload. So if your data is already compressed on the application side, probably we cannot compress it by much. But on many cases it can reduce network cost. So make sure to enable compression. If you're using Scylla Cloud, we are doing that for you. The last thing I want to show is actually not a change in the Scylla database itself, rather in the way that you can deploy ScyllaDB in Scylla Cloud, or can use Scylla Cloud. So originally, and that's by the way still the default, every deployment that Scylla Cloud have on a data center is automatically a stretch between availability zone, 3 availability zone. So we can have in this example 3 data center, each of them have 3 availability zone. That's great, that's give you a lot of high availability. You can support, or if there is a problem in one zone, for example, US East 1C, the rest of the data center can continue to work as is because you still have a quorum. But the downside of it that you do pay not just for the communication between the data center, you also pay for the communication inside a region between the zones. Because as you might know, AWS and other cloud providers charge for that. In recent version of Scylla Cloud, we allow you a more flexible deployment choices, and what you can actually do is deploy the entire region in the same zone. You can do it in all regions or in part of the regions as I'm showing here. And of course, as a trade-off, this architecture will reduce the network cost and the amount of data you need to send between zones, but it's slightly less available. So our recommendation is to only use that when you have more than one region. If you have one region, I highly recommend using at least 3 zones. I hope it makes sense. Last part of our session, I talked about Scylla Core, I talked about Scylla Cloud. Now I'm going to cover briefly what we are planning to do, some of the things that we're planning to do in 2025 in the scope of reducing cost. We're doing other things which are not related to cost, but this is about cost. And the first one is about object store. So first, let me briefly describe the difference between the store that we're using right now in object store, like S3. So today we are using NVMe on EC2, for example. It's a local SSD, very fast, super low latency, much lower than a sub-millisecond. It's inferior, and it's pretty expensive, maybe not to other alternative like EBS, but compared to S3. S3 is remote, so latency, of course, is much higher. It can get to tens of milliseconds on some cases. It's persistent, it's even highly available, but the cost is low. So far we already use S3 for backups, but not for actual live data. And this is something that we are working on right now in Scylla Core and Scylla Cloud. So the idea is to keep some of the tablet local and some of the tablets of one table, some of the tablets or SS table local and some on the cloud on S3. Actually, everything is on the cloud, but on S3. And if you're using a compaction strategy like time window compaction strategy, you can set which date, for example, will be on the SSD and which will migrate to object store. One example can be that you want to keep the last week on SSD, the last 2 months on S3, because the assumption here, and if this assumption is not true, maybe you don't want to use it, but the assumption is that the latest data is more hot, you access it more frequently and in low latency, but as the data age, like all of us, it becomes slower and you probably need to access it less frequently, and you are fine with paying with latency in case you do want to access this kind of information. So we are working actively, and I hope it will be available very soon, tier storage with Scylla, with time window compaction strategy. The second part of thing that will help you reduce cost on the cloud, and this is actually already available on Scylla Cloud. So it's when I created the deck, it was a plan, but now when I'm presenting it, it's already available, and it's more flexible pricing. So, and this is true for many type of services on the cloud. You usually have at least 2 types of pricing model. One is on demand, use whatever you want and pay the highest price, but you don't have to pay anything in advance. The other extreme of it is reserved. And this is true for DynamoDB, for when it's called provision, or for EC2 when it's called reserve, or on many other plans, the same on GCP. On reserve, you allocate in advance the resources and you use only what you allocated for. And I will show it in a graph in a second. Flex credit is a middle ground for that, and I will demonstrate it right now. So let's start with on demand. On demand, if you go to Scylla Cloud, provide your credit card and start using it, you will pay for what you use, only for what you use, but that will be the highest price, because on demand, if you're looking at the pricing, it's the highest. That might be fine, but if you're using more and more resources, you probably want to use a lower tier of price. Here come reserve pricing. So on reserve pricing, for example, you allocate 3 machine, 4 machine, whatever you think you need in advance, and you work under it. Of course, The downside of it that you need to think how much you're gonna need and allocate it in advance, and you need to pay in advance. But you get the best price. The middle ground, there are actually two points in this trade-off. One is you can reserve a little bit less than what you actually need, or maybe you did a mistake when you calculate how much you're going to need. The extra that you are using on top of the reserve will not kill your cluster if, for example, the storage is exhausted. You can imagine the blue line is a storage. Rather, Scylla Cloud will automatically scale the cluster for you, but you will have to pay on-demand price, the highest price, for this extra usage. This might be fine, by the way, for many cases, and also you can sleep better at night knowing that if the cluster did scale beyond the reserve capacity, we will scale it for you. We wouldn't hurt the high availability of the cluster. But now there is a better option, and it's called Flex Credit. On a Flex Credit, you do pay in advance, but you don't allocate resources in advance. You pay in advance that in the case that you are going above your reserve, you will pay with a better price. So with that, you can actually allocate a smaller chunk of reserve capacity, because you know that in case you are going on top of that and beyond that, you will pay more, but not as more as on demand. So that's another pricing option that you can consider. And of course, I'm sure our sales team will be very happy to explain all the details and all the use cases. And if you go to Scylla Cloud, you will, or very soon you will, see all this option, and you can choose it interactively from API or from the GUI. The last thing I want to mention around pricing is the DynamoDB 50%. It's a special kind of pricing for people migrating from DynamoDB to Scylla. I didn't mention it earlier, but Scylla is compatible with both Apache Cassandra and DynamoDB APIs. So it's easy to migrate from each of them. And DynamoDB 50 is a great opportunity for people using that, and there is a link in the presentation. Okay, I feel I talked very fast, but let's try to summarize the last 30 minutes or so. So the session was about reducing cost in the cloud, and I tried to prove that you can do it with Scylla in 3 parts. First, I explained why Scylla core database was engineered to reduce cost using high performance and high throughput in particular. Then I explained how Scylla Cloud is designed as a cloud service that allows you to reduce costs through different deployment type, network compression, fast scaling, etc. And last, I show a few flexible pricing options that can help you choose the right pricing model for you, that can help you pay less and sleep better at night. And with that, I want to thank you.